Instead of using paths to denote the location of our strain gauges, we can average over areas by applying surface elements. To do this, we first need to open the geometry window. Select inch as your unit. Next, click Generate. The imported CAD file now appears. Click on the XY plane. This plane is centered about the support hole, but on the rear face of the crank. Our strain gauges are going to be placed on the front face of the crank. Therefore, we need to define a new coordinate system aligned with the center of the support hole, but along the front face of the crank. To do this, click on New Plane. Since we had the XY plane selected when we clicked New Plane, it defaulted the type of plane to a from plane and the base plane as the XY plane. That's what we want. Under Transform, we're going to select Offset Z. And for the value, we're going to put 0.375, which is the thickness of our crank. We do not need to change the X or Y values because we still want our new plane to be centered about the hole. Click Generate. We now see that we have a plane centered about the support hole but on the front face of our crank, which is what we want. Selecting this plane, we want to click New Sketch. Open the Sketching tab. Click on the Z-axis to look directly at the face. For this example, we're going to assume that the strain gauge is not perfectly vertical or perfectly horizontal. To draw this kind, we need to use a rectangle by 3 points drawing tool. We're going to place the strain gauge arbitrarily. Click in one location, zoom in, click in another location, and then drag down to create our strain gauge. Next, we need to dimension our gauge. The width of the gauges used in the strain gauge rosettes you'll be given is approximately 0.063 inches. That's going to be our L1. In the Details view, enter that value. The length of the gauges you'll be given is approximately 0.083. That will be our L2. Next, we'll enter that value. Next, we'll define an arbitrary vertical distance between the center line of our crank and one of the points that we've just drawn. Set this to 0.25. It would be easy to draw an entire strain gauge rosette right now by adding 2 additional rectangles, one to the left of the central rectangle, one to the right. They would each be inclined at 45 degrees relative to this central rectangle. For the simplicity of this example, we'll just stick with one strain gauge though. Now that we're done drawing and dimensioning our strain gauge, we're going to click Generate. Next, click on Concept, Surface from Sketches. click on Sketch 1 in the tree outline, come down to the Details view and click Apply. Now click Generate. We've now created a surface body with thickness of 0 that sits on top of our crank. Exit the Design Modeler. Next, we're going to open the mechanical window. When you're prompted to update the upstream data, click Yes. When the mechanical window opens, come over to the outline window and expand geometry. Here we see that we now have two pieces of geometry. Select the surface body. It wants you to give it a thickness. It doesn't matter what this thickness value is for the purpose of the experiment, so we'll enter a small value of 0.001 inches. It defaults the material to structural steel. We don't need to change this because it will be ignored in our analysis. Next, we need to check on the connections. Sometimes connections will automatically be formed between our new surface body, which represents the gauge, and our existing crank. If they do not, right-click on Connections, Insert, Connections Group. Right-click on Connection Group, Create Automatic Connections. Expand the Contacts folder, and click on the Generated Contact. It should have created a bonded contact between the face of the crank and our surface body. Under Advanced, the formulation should be Pure Penalty. If it is not, change it to that. Next, come back to the Geometry section of the outline window. Right-click on our surface body, Insert, Commands. We'll now type 2 lines of commands, which will affect how ANSYS treats our surface body. The first line is ET, MATID, 181. That tells that the surface body should be meshed with elements of type 181, which is just one of the elements in the element catalog. Press Enter. The second line is KEYOPT, MATID, 1, 2. This is a specific command for element 181, and it tells it to have a stiffness of 0. For more information on these elements, see the Help menu under Mechanical Help and search for element 181 or solid 181. Next, we need to change our mesh. Right-click on Mesh, Insert, Sizing. Make sure you have the Edge Selection tool chosen. Zoom in on the area that contains your strain gauge. Select one of the vertical sides and one of the horizontal sides of your strain gauge. Click Apply. Next to Type, select Number of Divisions. This defaults to 1, and that's the value we want. This will map our surface body, which represents the strain gauge, with only a single element, which will make analyzing our results very easy. Next, right-click Mesh, Insert, Mapped Face Meshing. Select the face of our strain gauge and click Apply. Right-click Mesh, Generate. We see that our surface body was meshed with only a single element, and that element is overlaid on top of the mesh for our crank. If you had previously defined your fixed support and force vectors, you might need to reset where they're applied to. Click on Fixed Support, zoom out. For the geometry, select your support holes. Click Apply. Click on Force. Select the holes on which the force is applied. Click Apply. Next, click on Solution, Insert, Coordinate Systems, Elemental Triads. Next to Geometry, it will say that it has all bodies selected. Click on this, and instead select just the strain gauge body using the Body Selection tool. It may be difficult to select just this body. If you have trouble, you can suppress the crank body momentarily in order to select this body and then unsuppress the crank body. Usually zooming in far enough will allow you to select this surface body though. Click Apply. Elemental Triads will show us the coordinate system for each individual element, which will make analyzing our results much easier. Next, we're going to right-click Solution and hit Solve. Notice that we haven't inserted the strain yet, and that is because we need to see what the elemental triad is for the single element that makes up the surface body. Once the solution is finished, click on Elemental Triads. You may need to zoom out. Now remember that this edge here was the side of our strain gauge, and this edge here was the top edge of our strain gauge. Therefore, the value that we're interested in is the strain along the y-axis of this element. Next, right-click on Solution, Insert, Strain, Normal. For geometry, select just the strain gauge body. For orientation, we're going to select the y-axis, as we just learned by looking at the elemental triad solution. Under coordinate system, we're going to switch from the global coordinate system to the solution coordinate system, which will use the coordinates that we saw in the elemental triads. Next, right-click Solution and hit Evaluate All Results. Notice that we don't need to resolve. All it needs to do is extract the strain data from data that we've already collected. this solves very quickly. Click on normal elastic strain. We see that the minimum and maximum values are the same. In this case, 15 microstrain. This is because there's only one value, since we only have one element. The strain on this surface, which represents our gauge, was extracted from the strain at the nodes of the underlying mesh of the crank. There's no need to do a transformation on this value, since it's already along the axis of interest to us. This value can be compared directly to your experimental data.